Hello and welcome. How many sheep does it take to make one wool sweater? I'm joking, of course. Sheep can't knit. In this video, we're going to go back in time and review a technique that you learned in Calculus 1. It's a family favorite, integration by parts. Here we have the integration by parts formula. The integral of u dv equals uv minus the integral of v du. You proved this back in Calculus 1, but I'll just mention that you might recall it comes from the product rule for derivatives when you go about proving it. Now remember, the goal is to take an integral that you can't do and turn it into an integral that you can do. So the integral of u dv is the integral that you're starting with, and then when you take this integration by parts step, in other words, write the right-hand side, you're going to have this integral that hopefully you can do. Hopefully it's an easier integral to figure out. That's the general goal of integration by parts. There are other uses of it, but this is the main goal here. So turning over to example 1, we've got the integral of x squared e to the x dx. Now what we do is we identify what we're calling u, identify what we're calling dv, and we'll remind you of the mnemonic in just a second to help remember good choices for you. Good choices for you. And but here we're just going to use u equals x squared, and dv will be all the rest of it. And then you might remember making a little table here. So you write u equals x squared, dv is the rest. And to finish the little table of stuff over here, you want to look at the right side of the integration by parts formula. You have the v that you need, that we don't have yet. There's the v again, and then we need a du as well. So to get the du, we take the derivative of u with respect to x. That's going to be 2x dx. That part of it kind of looks like the substitution method if you cover up the dv, but this is a totally different method than substitution. In fact, you're never substituting the variables at all. You'll notice when we take the next step, we're never entering into the new variable u. So then we can, to find v from dv, we can integrate. So the integral of e to the x is e to the x. Sometimes it's hard to tell if you're taking the derivative or integrating e to the x because they both look the same, but here we're integrating the dv, so integrating the e to the x to get v, which is e to the x. And now we're going to follow the right-hand side of the integration by parts formula. We're going to write uv minus the integral of v du. I'm going to draw little arrows here to represent what we're multiplying. We're taking u times v, and then we're going to do minus the integral of v du, which is the bottom row right there. So the uv is along that little diagonal going down to the right, and then the last row is what goes in your new integral. So here's uv, x squared e to the x, and we have minus the integral of v du. And I'm shuffling around a couple of the factors there. I put the dx at the end just to make it look nicer. Now this new integral, we can again use integration by parts on. Notice that we've gone from an x squared down to an x. So maybe if we take one more integration by parts step, then we can bring this x down to just 1, or the 2x down to a 2. So what we're going to do is let u equal 2x, and then we'll have dv equals all the rest. So this is the next integration by parts that we're using, another one. So then we'll complete our table. We have du equals 2 dx, integrate e to the x to get e to the x, and we'll use the integration by parts formula, and I'm just drawing those little arrows again to remind us that we're doing uv minus the integral of v du. Now that integral explodes into two terms, so we're going to have to open up parentheses because we're subtracting both of those terms. We're subtracting the entire result of that integral exploding into different terms. So the uv is going to be 2x e to the x. We'll put the minus, and then we have the integral of 2 e to the x dx. Okay, so now what we can do is distribute that negative. We're going to distribute the negative in, and we get x squared e to the x minus 2x e to the x plus the integral of 2 e to the x dx. Now, when we look at this new integral, this is doable. This is the integral of basically e to the x, which is just e to the x. The 2 is just a coefficient that hangs around. So this would give you x squared e to the x minus 2x e to the x plus 2 e to the x, and then don't forget your plus c at the end. Okay. Now let's look at a way of streamlining the integration by parts method. If you look at what we did, there's a lot of fluff here. There's a u equals, a du equals, a dx, a v equals, a dv equals. There's a lot of stuff that maybe we don't need to write over and over again. And there's some repetition. There's a 2x e to the x right here. So the du, the v du that appears in our new integral can then be broken apart again into u, so we're going to let u equal to 2x, and then the new dv we're going to let to be e to the x. So it's kind of like we can just take what was the v du from the first integration by parts step, and then for the next integration by parts step we turn it around and we say those are the same things that are going to be our u and our dv. So the key things going on here are the x squared, the e to the x, the 2x, which is repeated here, the e to the x, which is again repeated here, and then we have the 2 and the e to the x. And so these are really the key parts that we would want to write down. So when we go down here looking at this thing called tabular integration, all tabular integration is a streamlined way of writing integration by parts. So sometimes people ask, like, what's better, tabular integration or integration by parts? And the answer is, I mean, they're really the same thing. They're exactly the same thing. They're both integration by parts. It's just that the tabular integration way, tabular integration is a way of writing integration by parts in a very streamlined way. Let's give an example by doing the same exact integral. So we're going to look at the integral of x squared e to the x. This is for example 2. And we're going to do exactly the same, so we're doing exactly the same integral, but just written in a streamlined way. So rather than writing u equals x squared, we're just going to write x squared. Rather than writing dv equals e to the x dx, we're just going to write e to the x. Then what we're going to do to perform integration by parts repeatedly is take the derivative going down on the left, integrate going down on the right. And so if we pulled out of integration by parts at this point, or the tabular method, then we would have exactly what we would have for the first step that we took up here. We would have x squared e to the x minus 2x e to the x dx. So we would get to this step. But since we know we're going to turn around and do another integration by parts, let's go ahead and do it. Starting from this row, so this row right here is now representing u and dv for the second integration by parts. So then we'll again take the derivative on the left, integrate on the right, and that's another step of integration by parts. And it turns out we can go all the way down to even 0. We didn't even do it in example 1, but we can do another integration by parts if we wanted to. Take the derivative on the left, integrate on the right, and that would be another integration by parts. Now the UVs that are popping out are along the diagonals. So the UVs are along the diagonals, right? If we think about the first UV is x squared e to the x. That was along this diagonal right here, x squared e to the x. Now the next UV that we got came from this second integration by parts that we did, and that's again in a diagonal. It's the 2x e to the x. There's the 2x e to the x with our tabular method. Now the only thing about that UV is that there's a negative sign in front of it that's going to flip the sign of that UV. So notice how when we did the second integration by parts, this integral exploded into a UV right here. That's the 2x e to the x. minus the integral of 2x e to the x dx. So the main thing is that this uv, this second uv from the second integration by parts, has a negative in front of it. And that's just because of the negative symbol in front of the integral from the first integration by parts. And if we did integration by parts again, we would get the next uv, which is going to end up being 2 e to the x. It's going to have two negative symbols in front of it. It's going to have the negative symbol that's in front of the integral from the first integration by parts, and then another negative for the integral in front of the second integration by parts. So actually, if you keep doing integration by parts repeatedly, the signs in front of the uv are going to flip: positive, negative, positive, negative, positive, negative. So they'll always start out positive, but they're going to flip: positive, negative, positive, negative. Now, depending on what you have for your u's and v's, that might also influence the sign. Like if you had a -2 here, well then -2 times e to the x times positive 1 would still be negative. But these sign flips are going to affect the signs of the UVs. So now that we have all the UVs, and if we think about this last integration by parts, if we pulled out of integration by parts, what would go inside your new integral would be 0, right? It would be e to the x times 0. And the integral of 0 is just a constant, c. So, but usually we're not going to write that out. We're just going to leave it like that and write out all of the UVs, x squared e to the x, minus, and then the next diagonal we have 2x e to the x. The next diagonal we have 2 e to the x, and then plus c. We don't want to forget about our plus c. So just so you have it down in your notes, remember that you're differentiating going down, and on the left, and then you're integrating going down on the right. So that's a much faster way of doing integration by parts, especially if you have to do integration by parts multiple times, like we did in example 2. Another thing is that if you have a polynomial as your choice for u, notice that if you continue taking derivatives on the left, that polynomial will eventually become 0. The powers will keep coming down when you use the power rule for differentiation. And so eventually you're going to get a constant, and then the derivative of that constant will be 0. So if you have a polynomial as part of your integral, and you're using integration by parts, then letting u equal that polynomial is possibly a good choice, because the derivatives will eventually go down to 0. Let's do a couple more examples. Example 3 is the integral of ln x dx. Now, one thing I wanted to mention is, before we do this, is that there's a mnemonic that goes along with integration by parts. And this is just a common mnemonic that a lot of students use. It's liate, and I'm writing it vertically because we're going to go to the right and write out what each of these letters stand for. So the L stands for log, or like logarithm. That's a good choice for you, and the reason is that the derivative of logarithms gets simpler in the sense that they become, well, a derivative of natural log of x becomes 1 over x. And that x on the bottom of that fraction could possibly cancel with other x's, thereby simplifying the integral, the new integral that you get. So logarithms are a good first choice for you if you have them. The next is I, which stands for inverse trig functions. So this would be things like inverse sine, inverse cosine, those kind of things. Inverse tangent. I should probably write up logs. Logs are like ln x, log base 2 of x, things like that. So inverse trig functions, again, when you let u equal to those, the du that you're going to get is going to be simpler in some sense. It'll be 1 over the square root of 1 minus x squared in the case of inverse sine, but that's better than just getting stuck with inverse sine itself. So at least it changes the form of your function. A stands for algebraic functions. And here what we mean is polynomials. Like x squared or x cubed, things like that. It could even be a full-on polynomial, like x to the 5th minus 3, x to the 4th plus 5, x cubed. could be things like that. You can let u equal to that whole polynomial, because eventually the derivatives of polynomials go down to 0. Then the last two are actually equally bad, trig functions and exponentials. Trig functions, which would be like the regular sine, cosine, and things like that. Those are bad because when you let u equal to those trig functions, when you keep taking derivatives, they don't really get any simpler. Also, exponential functions, the same thing happens. This is like e to the x, 2 to the x, and so on. All of these are good choices for u. Good for you. they're good choices for you. I never thought about that in all the years of teaching calculus 2. Good for you. Oh boy. I'm glad I caught that one on film. Okay. So we're going to use the tabular method just to get practice with the tabular method version of integration by parts. So I recommend that for Calculus 2, for Math 181, that you learn and that you practice using the tabular method, because it's going to streamline your whole integration process. You don't want to be stuck in an integral trying to figure out how the integration by parts is going to work and not having enough room to write it, or just taking a lot of extra time to figure out how to solve it using integration by parts. You want to be able to do it as quickly as possible. These kind of things, evaluating integrals, you want to be able to do as quickly as possible. This will be like the smaller part of a larger problem later on. So off to the right here, we're going to write the choice for u, which is going to be logarithms, logs. Logs are good for you. And then we're going to, on the right side, in the right column, there's not really anything left over here except for just a 1. You could always say there's like a times 1 in front of the dx. So we can write a 1 there for the dv part of it. So the derivative of ln x will be 1 over x. The integral of 1 will be x. And we're going to pull out of integration by parts here. Now the diagonal is going to be where the uv is still, and I'm going to put a little plus there as a reminder. And then we're going to pull out of integration by parts, and I'm going to put this minus here as a reminder that that's the sign that's going to be in front of the integral that we have left. This is especially helpful if you do integration by parts a couple of times and then pull out, like we're going to do in example 4. All right, so the uv is going to be x ln x. Then we have the minus because of this minus symbol right here, and then the v du. So we have x times 1 over x dx. So notice how the ln changed form when you took the derivative of it. Changed into 1 over x, and see how this 1 over x is going to simplify with this x here. It can interact with that x and simplify. In fact, x times 1 over x is just 1. And a lot of people don't even write the 1 there. They'll just write the integral of dx. So I'm going to write that. I'll slide the dx over closer to be with the integral symbol. They just want to be together right now. All right, so the integral of dx is going to just be x. Because remember, you can imagine like a little 1 right there. The integral of 1 is x. And then don't forget your plus c. Okay. So example 4, we have the integral of e to the x cosine x dx. Now when we look back up at our choices for u, here we have a trig function, cosine x, and an exponential function. And both of these are pretty much equally bad. So we can use the exponential function for our u or the trig function. It doesn't really matter. Let's go ahead and use the exponential function. Again, doesn't matter, but I'm going to write it with the exponential function as our u, so that's going to be on the left, and then cosine x will be on the right. That's going to be our dv. Now we're going to take one step of integration by parts. We have e to the x, and then sine x. Remember, we're taking the derivative of e to the x and then integrating cosine x to get sine x. Now, when we look at this, if we pulled out of integration by parts at this point, so I'll just go like this. If we pulled out at this point, we would have inside of our new integral e to the x sine x, which is not really any simpler, and it's even, it's different from the integral that we started from, but it's not really simpler. But let's take one more step and see where this leads us. So we're going to take another step of integration by parts. We'll have e to the x, and then we'll have negative cosine x on the right. Now if we do another step of integration by parts and pull out, notice what's inside of our new integral. My voice changed there. Our new integral has e to the x cosine x. It's getting late, so I'm getting a little silly. Sorry about that. So we have e to the x cosine x inside of our new integral. But wait a minute, that's what the integral that we started with. This is kind of weird. It loops back around. And you might remember that this weirdness is actually a good thing. Let's pull out of integration by parts and see what we mean. Remember that the UVs are going to be alternating signs, and that last integral is going to have the next alternate sign in front of it. So we're going to pull out, and I'm going to actually write down this integral again as being the left side of the equation. So like this integral is equal to, by doing the integration by parts a couple times, e to the x sine x. That's the first UV. And then you have e to the x times negative cosine x times an extra negative to make this plus e to the x cosine x. And then the integral sign is going to be negative because you have a negative and then this positive and this positive, so that's negative altogether. And then we have the integral of e to the x cosine x dx. So now when we look at this, we have on the left side of our equation the integral of e to the x cosine x dx. On the right side of the equation we have the same thing, but we have a negative symbol in front of it. Let's get these two together by adding the integral of e to the x cosine x dx. So here we're abstractly thinking of this integral as some big chunk. It's just representing, if we had numbers, this would be just a number. I mean, symbols and its variables, but it's representing some kind of mathematical quantity here. And we can add that quantity to both sides of the equation, just like you would do with algebra. In fact, sometimes you'll see in the books that they'll represent this whole thing, this integral, with I, and then this integral with I as well. And then you're just adding I to both sides, I standing for integral. We're not going to do that here, but just know that you can do that. Great. So on the left side we have one of those integrals plus another one of those integrals. That's two of the integrals. And as our last step, we're just going to divide that 2 over to the right side. So we'll have the integral of e to the x cosine x dx equals 1/2 e to the x sine x plus 1/2 e to the x cosine x. And we do have an indefinite integral here, so what do we have to put at the end here? A plus c. C for celebration. So I hope you enjoyed the review of integration by parts. And thanks so much for watching. See you next time.